learning about different sequences, it is quite easy to see that if Hn was the sum of two different sequences, let's say Fn plus Gn, for every n greater than or equal to 0, then delta Hn is equal to, by definition, Hn plus 1 minus Hn is equal to Fn plus 1 plus Gn plus 1 minus Fn plus Gn is equal to Fn plus 1 minus Fn plus Gn plus 1 minus Gn is equal to delta Fn plus delta Gn. Right? And therefore, inductively, it follows that the same should hold for delta to the n Hn is simply going to be delta to the n Fn plus delta to the n Gn, right? Because delta Hn is equal to delta Fn plus delta Gn. Both of these are new sequences. You can get it by induction. And in fact, if C and D are constants, then delta of Cfn plus Dgn is equal to C times delta Fn plus D times delta Gn, right? The easy thing is just put it in this. You can pull out the C from Cfn plus 1 minus Cfn, right? And you'll get exactly this, right? And this to the P, well, maybe I shouldn't have used N here. This should have been a K or P, whatever. The book uses P, I'll use P. P, delta to P. Delta to the P, C times Fn plus D times Gn is equal to C times delta to the P Fn plus D times delta to the P Gn, right? Such a thing is called linear this is called the linear property of differences. Linear property of differences, ERE. And this means that delta is a linear transformation, okay? But let's not get too much into that. Therefore, delta is a linear transformation. If you know what that means, then great. Basically, it exactly means this, that it preserves C times Fn plus D times Gn as C times delta Fn plus D times delta Gn. Okay? Now, we want to know what things get mapped to 0. What does delta to the P map to 0? Map to 0. Right? We saw that there's at least some sequences that get mapped to 0. Right? We saw that n squared was getting mapped to 0 by delta cube. We want to know what would delta P map to 0. Theorem. Given any polynomial f of x, given any polynomial f of x of let P is equal to degree f. Let P is equal to degree f. Okay? Consider the sequence. Consider the sequence Fn where n is equal to 0 to infinity. Right? I'm looking at f of 1, f of 2, f of 3, f of, well, starting from f of 0. So f of 0, f of 0, 1, f of 2. Consider this as the sequence. Then delta P sends this sequence. Then delta to P sends this sequence to 0. Okay, proof. We are going to use induction. By induction on P. Okay, first let us look at case P is equal to 0. Case P is equal to 0. Well, this is trivial, right? Only thing, well, if the only degree 0 polynomial is a constant and delta P plus 1, not delta P. Okay. Only degree 0 polynomial is a constant. Therefore, delta f of n is equal to 0 for every n, right? Therefore, delta sends delta to 1 in this case. 1, which is 0 plus 1, sends f to 0. Right? So assume that it works for p is equal to n. Assume true for p is equal to k. Then we want to show this for p is equal to k plus 1. Want to show, or actually let me do this, k minus 1, want to show for p is equal to k. Okay, I just don't want to do the extra work. It's going to be exactly the same. So write f of x is equal to, well, it's a polynomial, so you get a0 plus a1x plus a2x squared plus blah 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 ap x to the power p. Okay, so fn is going to be a0 plus a1x, a1n plus a2n squared plus dot 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 plus ap n to the power p, right? Well, from what we have seen before, therefore delta to the p plus 1 of fn, the sequence n is equal to 0 to infinity, is equal to, by my linearity of differences, is equal to summation k is equal to 0 to infinity a k. Oh, well, this was a bad idea. Infinity, let me use a j maybe. A j is equal to 0 to infinity a j delta to the p plus 1 of n to the power j. N to the power j, where n is equal to 0 to infinity. This power should be, this power should be p. My bad. P. Okay, now I am going to say it suffices to show, therefore suffices to show delta to p plus 1 of n to the j, n is equal to 0 to infinity, is equal to 0, right? It's going to be a sum of 0 times some sequence, which is 0 times anything is 0, add them together, you still get a 0, right? So I want to show that n to the j is 0. In fact, it suffices to show that it is true for the highest power, n to the p, n is equal to 0 to infinity. Because if it is true for this power, it is going to be true for everything less than it. Okay? Therefore, let hn is equal to n to the power p. Therefore, delta hn is equal to n plus 1 to the power p minus n to the power p, which is equal to, therefore, delta Hn is equal to, since we know the binomial theorem, I is equal to 0 to p, p choose I, n to the I, right? Minus n to the p. Well, what I'm going to do is I'm going to separate out the term for n to the p. So I get I is equal to 0 to p minus 1, p choose I, n to the I, plus n choose n, which is n choose n times n to the p minus n to the p. Well, n choose n is just 1, so this is equal to just some polynomial g of n, where g of x is equal to summation. So let me just say is equal to 0, where g of x is equal to I is equal to 0 to p minus 1, p choose I, n to the I. Whoops. Not n to the I, x to the I. Great. I have a polynomial, but what is the degree of this polynomial? Therefore, g of x is a polynomial of degree p minus 1. And since I have assumed that my induction result holds for p minus 1, therefore delta to the p of g of x is equal to 0. Well, of g of n is equal to 0, and therefore delta to the p plus 1 of h of n is equal to delta to the p plus 1 of n to the p is equal to 0. 0 sequence. And therefore, by induction, delta to the p plus 1 of fn is equal to 0. Okay, and so that shows me that if my polynomial has, wait, did I call it fn? Did I name it something else? What was f? Oops, bracket n. F bracket n is equal to 0. Okay, so this shows that, oh, if I have a certain sequence and it is given by a polynomial, then after taking the difference, polynomial of degree n, after taking the difference n plus 1 times, it is going to be 0. Okay, let me now define what is called a diagonal sequence. Okay, so given a sequence Hn, construct the difference table. Construct the difference table. Well, it's going to look like H0, H1, H2, H3, H4, H5, ... Delta of H0, delta of H1, delta H2, delta H3, delta H4, ... delta squared H0, delta squared H1, delta squared H2, delta squared h3. Hey, these should be like, okay, maybe I'll just write it in the proper place. Delta h3 and delta h4, so on. I'm going to get delta cube h0, delta cube h1, delta cube h2, delta cube h3, dot 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 dot, delta to the 4 h0, and so on. I'm going to get some terms here, some terms there, delta to the 4 h1, whatever. This sequence that I'm going to get is called the difference diagonal. Difference diagonal. Okay. So what is the difference diagonal? The corresponding difference diagonal, the corresponding difference diagonal is equal to delta to the n h0 from n is equal to 0 to infinity. Okay, so for example, let hn is equal to n choose 3. Okay, n greater than or equal to 0. Well, what does find the difference diagonal? Find the difference diagonal. Okay, what does it look like? Solution. Well, let us look at the difference table. 0 choose 1, 0 choose 2, sorry. 0 choose 3, 1 choose 3, 2 choose 3, 3 choose 3, 4 choose 3, 5 choose 3, dot dot dot. I'm going to write in red what their values are. This is 0, this is 0, this is 0, this is 1, this is 4, this is 10, and so on. Okay. Well, let us look at their differences. 0, 0, difference is 0, 0, 0, difference is 0, 0, 1, difference is 1, 1, 4, difference is 3, 4, 10, difference is 6. I'm going to tell you that the next difference is actually, next one is 6 choose 3, which is 20. 10 and 20 have a difference of 10. Okay. Let us look at the differences again. So let me write this down. This is delta 0 hn, delta 1 hn, delta 2 hn, 0, 0 gives you 0, 0, 1 gives you 1, 1, 3 gives you 2, 3, 6 gives you 3, 3, 6, 10 gives you 4. You can see a pattern developing. Delta cube hn, 0, 1 gives you 1, 1, 2 gives you 1, 2, 3 gives you 1, 3, 4 gives you 1, and so on. Delta to 4 hn, 0, 0, 0, 0. And now, if you see, whatever I do, this difference is constantly going to be 0 for everything afterwards, right? Because I know that after, since n choose 3 is technically like a polynomial, right? N choose 3 is n into n minus 1 into n minus 2 divided by 6, which is a polynomial of degree 3. It is going to get annihilated by delta to the 4. Everything after that is going to be 0. Therefore, the diagonal sequence is equal to 0, 0, 0, 0. I'm starting from delta to the 0. So 0, 1, 0, 2, 0, 3, 0, then a 1. 0, 0, 0, 1, 0, 0, 0, dot, 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 dot. Okay? Well, here it just turned out 0, 0, 0, 1, 0, 0, 0. Is there a pattern? Yes, there is. Lemma. Fix any integer, fix p greater than or equal to 0. For the sequence, n choose p, n is equal to 0 to infinity. The corresponding diagonal sequence, diagonal sequence is, let us try to guess. For 3, it was at the 4th place. Where would you get? 0, 0, 0, dot, 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 0. Oops, that should have been a 0, 1, 0, 0, 0, 0. Where this is the term AP with in pth place is equal to 1 when starting from A0. Okay, so, or my bad, the usual convention is calling it CP, so let me call these CP. CP is equal to 1 and starting from C0. Okay, so the pth place has a 1. Okay, proof. Denote the diagonal sequence. Denote the diagonal sequence. Diagonal sequence by Cn. Cn, n is equal to 0 to infinity. Okay, then we want to show Cn is equal to 0 if n not equal to p, 1 if n is equal to p, and greater than or equal to 0, right? So now you construct the difference table. Construct difference table. What is it going to look like? 0 choose p, 1 choose p, dot, 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 dot. P minus 1 choose p, p choose p, p plus 1 choose p, p plus 2 choose p, dot, 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 dot. Right? Now, an important thing to keep in mind is that, well, let me write the values in red for this one. Again, all of these are 0. Then you hit a 1. Then you hit a p plus 1. Then you hit what do you get? P plus 2 choose p is going to be p plus 2 into p plus 1 over so this is going to be p plus 2 into p plus 1 over 2 and so on. Okay, let us construct the difference table. This is giving you 0, 0, 0, 1 p, and then this gives you p plus 2, p plus 2, p minus 1, p times p plus 1 over 2. Okay. Well, 0, 0, 1, p minus 1, and this is going to give you p minus 1 over 2 times p. So this became p minus 1. This was p choose 1, p choose 2. This became p minus 1 choose 1, p minus 1 choose 2. Okay? Sorry. Yeah. You continue this, you're eventually going to get 0, 0, 0, 1, 2, dot, 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 which will give you 1, 1, 1, dot, 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 dot in row P, and the final row would all be 0, 0, 0, 0. Okay? And so, oops. Therefore, Cn is equal to 0 when 0 is smaller than or equal to n, smaller than or equal to p minus 1. Cp is equal to 1. And since n choose p is a polynomial, n times n minus 1 times n minus p plus 1, all the way over p factorial. Now, sure, p factorial is what is canceling out here, and I'm getting these numbers, right? But what is this? P factorial is a constant. The above thing is changing with n. So this is a polynomial in n with degree p. Therefore, delta to the p plus 1 sends n choose p, the entire sequence, to 0, which is why I could comfortably write this sequence as 0, 0, 0, 0 here because of this fact, right? And therefore, Cn is equal to 0 for every n greater than p. And hence, therefore, the only time where it is, therefore, Cn is equal to 0 if n is not equal to p, and 1 if n is equal to p. Okay, let's stop this video here.